DeepSeek's new model just passed a physics simulation test that was supposed to be impossible for AI, and it's forcing researchers to completely rethink what these systems can actually do. Now, before you think this is just hype, it's not. Let me explain what actually happened and why it matters way more than you'd think. So here's the context. Physics simulations are basically the nightmare test for AI. Not because they're hard to describe, they're actually pretty straightforward. The nightmare part is that they require something AI systems have historically been terrible at: genuine reasoning about how the world actually works, not just pattern matching from training data. Think about it like this. If I ask ChatGPT to summarize an article, it's doing something it's seen millions of times. But if I ask it to predict how a fluid will flow around an obstacle, or how a pendulum behaves under specific forces, I'm asking it to actually understand the underlying rules. Not memorize examples. Understand. For years, AI struggled here. Models would hallucinate answers. They'd get the math wrong. They'd confidently state something physically impossible. Researchers basically assumed that true physics understanding was one of those skills that required actual training in physics, the kind of training only humans could do. Then DeepSeek released their latest model, and something weird happened. It didn't just pass physics simulations. It passed them at a level that matched or beat specialized systems built specifically for this task. Systems that had been fine-tuned and optimized just to solve these problems. Let me break down why this is actually shocking. First, the benchmark itself. We're talking about tests like predicting the trajectory of objects under gravity, simulating fluid dynamics, modeling particle behavior, scenarios where you need to apply laws of physics correctly, not just guess based on what you've seen before. These aren't multiple choice. The model has to generate precise numerical outputs. Get the decimal place wrong, and you fail. Second, the scale. DeepSeek didn't build this capability with some specialized physics training module or a custom dataset of millions of labeled simulations. The model that's doing this is a general-purpose language model. It was trained on text and code, like any other large language model. Yet somehow it developed an intuitive grasp of physics that rivals systems designed from the ground up for exactly this job. That's the part that's breaking people's brains. Here's what researchers are realizing. These large models might actually be developing something that looks like genuine reasoning. Not in the sci-fi sense, not consciousness or true understanding in the human sense, but in the sense that they're building internal representations of how systems work, and they can apply those representations to novel situations they've never explicitly seen before. Why does this matter? Let me give you the practical angle. Physics simulation is everywhere. Drug discovery relies on simulating how molecules interact. Climate modeling simulates atmospheric behavior. Engineering uses simulation to test designs before building them. Materials science simulates how new compounds will behave. If AI can actually reason about physics, you're not just upgrading a chatbot. You're potentially accelerating research across every field that depends on simulation. That's not incremental. That's a phase shift. But here's the thing nobody's talking about. We still don't fully understand how DeepSeek did this. That's the real story. We have these models that are clearly doing something intelligent, something that looks like reasoning, and we're still largely in the dark about the mechanism. We can measure the input and output. We can see that it works. But the actual process happening inside, that's still a black box. And that should genuinely concern us, even if it also excites us. Because if we don't understand how a model develops physics intuition, we can't reliably predict what else it might develop. We can't guarantee it won't hallucinate. We can't be sure about its failure modes. We're basically in the position of having a tool that works better than we expected, and we're scrambling to figure out why. So what does this actually change right now? In the short term, it means researchers can start relying on these models for preliminary simulations and design exploration. Instead of running expensive computational simulations, you could ask DeepSeek to give you a rough prediction, then validate it with the real thing. That saves time and compute. Midterm, it probably accelerates research in fields that are simulation-heavy. Drug discovery, materials science, physics-based engineering. Any domain where you're currently bottlenecked by how many simulations you can run. Long-term, it's a signal that these models are developing capabilities we didn't explicitly teach them. That's the part that makes researchers nervous and excited in equal measure, because it suggests the ceiling on what these systems can do might be higher than we thought. But it also means we're building tools we don't fully understand. Here's the honest take. DeepSeek didn't break physics. The laws of physics are doing fine. What broke is our assumption that AI couldn't reason about physics without specialized training. And that's actually a bigger deal than it sounds. The lesson here is that we're still in the early stages of figuring out what these models can do. Every few months, something that was supposed to be impossible suddenly works. And each time, we're forced to update what we think is possible. That's not going to slow down anytime soon. If you want to actually keep up with breakthroughs like this without drowning in hype, subscribe. I break down one of these moments every few days. The stuff that actually matters, explained in plain language. No fluff, no corporate speak, just what you need to know to understand where AI is actually headed.